what we call condensed silicates. We discussed last time cyclic silicates, and then chain silicates, and then sheet silicates particularly, which have developed diverse type of structures and diverse type of layer, 2-layer structures, 3-layer structures, on combining with various types of layer hydroxides. And now we are left with the last thing, that 3D sheet structures and chain silicates and sheet silicates come into the category of 2D and 1D silicates respectively. And now we have the 3D silicates, where all the 4 oxygen atoms of the silicon unit, silicon tetraoxide unit, or shared between the neighboring tetrahedra, and you get a 3-dimensional lattice, which again we get different types of structures and different types of materials, depending upon the extent and type of the substitution that will happen. So simple 3D silicates don't have any metals, because there is no charge on the silicon lattice silica lattice as such, because every oxygen atom is shared and there is no negative charge on any of the oxygen atoms, and each oxygen atom contributes 1/2, because each oxygen atom is shared between 2 silicon atoms, so it contributes 1/2 to each silicon atom. So because there are 4 oxygen atoms, so each of them will contribute 1/2 to the silicon atom, and therefore the 4 halves is equal to 2 fulls, and therefore the formula of this silicates, 3D silicates, is SiO2. Formula of sand is SiO2. It doesn't mean that stoichiometry is SiO2. There's no discrete molecule like carbon dioxide. It's not a carbon dioxide type structure, discrete molecular structure. It's a 3-dimensional structure, and silicon and oxygen atoms are in the stoichiometric ratio of 1:2, and therefore we write the formula SiO2. That does not mean that SiO2 molecule exists as such. SiO2 molecule does not exist. So let's go to the presentation now. I will refresh the sheet silicates discussion that we had last time, and then we'll go to the presentation. Is visible for everybody?
Yes, sir.
Yeah.
Yes, sir.
So here we go. The sheet silicates, in which there are 3 oxygen atoms being shared between the neighboring tetrahedra. So one oxygen atom which was not shared was holding the negative charge, and the empirical formula for a sheet in which all the 3 oxygen atoms were shared became Si2O5 and 2 negative for 1 unit. And if you have n times, if this silicate sheet extends itself in 2 dimensions, length and breadth, and the formula becomes n times, and charge is 2n negative. So simple sheet silicates are rare, and they have complicated structures. We have 2 layers and 3-layer structures. They generate different types of minerals. One is clay mineral, colinite, we discussed it in detail, and pyrophyllite, they are the clay minerals. And then we have white asbestos, chrysotile, and biotite. Then we have micas. We have layer types of structures in the micas, which the examples are muscovite and margarite. And then we have the 4th class is morlite, which is bentonite, and verminoclite is the 2 examples. So we discussed last time that aluminum hydroxide and magnesium hydroxide form the layered structures in which the hydroxy groups occupy the sides on the both sides of a layer, and these hydroxide groups can be replaced selectively so that to match the oxygen atoms, the oxygen and the position of the oxygen atoms in the silicate layer, which is not shared. So silicate layer and aluminum hydroxide, these are held together. We have a double layer structure. This can be electrically neutral, provided you replace the OH negative, you dislodge the OH negatives from the aluminum hydroxide. So this layer becomes positively charged, silicate layer is negatively charged. So positive negative charge is neutralized and the double layer structure becomes electrically neutral. So the example of this type of structure is colinite. So we have aluminum hydroxide on one side and we have silicate sheet on the other side. This is monomer, therefore this holds two negative charge, and aluminum is 3 plus, OH is 4 plus, so 6 minus 4 is 2 plus, and therefore this two negative charge is balanced, counterbalanced by this aluminum hydroxide. So this is colinite, the mineral from which the bone china, etc., these materials are formed, the ceramic materials, all the sanitary ware or the plates and cups are ultimately prepared. So then we have silicate layer and aluminum hydroxide. Because aluminum hydroxide has this hydroxide on both sides of the layer, so you can have another silicate layer on the other side, and in between you have a sandwiched aluminum hydroxide, and you have three-layer structure. And pyrophilites are the examples. Now we have two silicate layers, therefore it is dimer here. It will be written as Si4O10 also. Obviously, this will have the 4 negative charge. So here is aluminum 6 plus and 2 negative, 6 minus 2, 4. So you have 4 negative here and 4 positive here and 4 negative on charge on this here. On the silicate layer. So again, it's an electrically neutral three-layer structure. So pyrophilites are three-layer structures, where colinite are two double-layer structures between silicate and aluminum hydroxide. So then we have magnesium hydroxides, silicates. When you can use the aluminum hydroxide layer, or you can use the magnesium hydroxide, because they are isomorphous in terms of the layer form, their ability to form a layer structure. So two-layer structure is again formed. The formula will be same again. Fi2, 2 negative charge here. Now magnesium 3 times, because it is 2 plus. So 2 is 6 plus. Again, OH is 4 plus. So this is 2 plus charge being counterbalanced by the 2 negative charge. So single layer, silicate, monomeric, single layer, and single layer of magnesium hydroxide. This is white asbestos. The combination of aluminum hydroxide with the single layer of the silicate generates the colinite, and combination of the magnesium hydroxide with single layer of silicate generates white asbestos mineral. And you have double layer of the silicate on each side of the magnesium hydroxide. You have three-layer structure that generates or talc or soapstone, which is slippery touch, and it has the formula of magnesium 3 times, now OH 2 times. In the same fashion as pyrophilite had aluminum 2 and OH 2, if you go back, this is aluminum 2 and OH 2. Here also magnesium 3, but OH 2 times. Again, this will have the 4 positive charge, and this is dimer here, Si2O5, or twice times 2 silicate layers, or you can write Si4O10. So this silicate double layer has a charge of 4 negative, and magnesium hydroxide has a charge of 4 positive. Again, counterbalancing the charge, and it is electrically neutral. Then you have the partial substitution in the three-layer structure of pyrophilite. Pyrophilite had this structure, aluminum 2, OH2, Si2O5, or you can write aluminum 2, OH2, Si4O10. This is the stoichiometric composition of the pyrophyllite is a three-layer structure. And then you can partially replace silicon atom in the silicate layers. There are two silicate layers on either side of the aluminum hydroxide layer. And if you do the partial replacement of silicon by aluminum, silicon is tetravalent and aluminum is trivalent only. Therefore, the silicate layer, or by each substitution, for each substitution of silicon by aluminum, the silicate layer accumulates one negative charge, because aluminum is 3 plus and silicon is 4 plus. So the replacement of silicon by aluminum generates a negative charge, which has to be balanced by some positively charged metal ion, which is then held between the layers, and you generate the mica minerals. So when you have partial replacement of silicon by the aluminum, you get negative charge in the silicate layer. That has to be balanced by some metals, which are then placed in between the layers, and that generates the mica. So we have this is muscovite mica, where the one aluminum has been replaced in this three-layer structure of pyrophyllite. One aluminum, Si3 now, O10. This has one negative charge, because one aluminum has been replaced, and here is aluminum, that one negative charge is counterbalanced by potassium, so it becomes a mica. Again, margarite has two aluminum atoms replacing two silicons, therefore it has aluminum 2, silicon 2, O10. Obviously, this has two negative charge, that is balanced by the calcium 2 plus. So that is the margarite mica. So substitution, this is substitution in pyrophyllite, which are three-layer structures involving aluminum hydroxide in between, and on either side we have silicate layers. So then the next is substitution in talc. Talc is again three-layer structure, which involves magnesium hydroxide instead of aluminum hydroxide. So formula of the talc is magnesium 3, OH2 and Si4O10. And again, if you have one aluminum replacing out of the four, 1/4 of the aluminum, 1/4 of the silicon, or in other words, we can also say one quarter of the silicon atoms being replaced by the aluminum throughout the sheet. So then you have the one negative charge here, that is again counterbalanced by the potassium outside on the outside. And when you have two when the aluminum in here is replaced, magnesium here is replaced by the iron, we have biotite or black mica. When you have the aluminum remains, 1/4 of the silicon replaced by the aluminum, and then you have magnesium being replaced by partial replacement of the magnesium by iron, which is also same layer structure, iron second particularly, because that maintains the integrity of the charge. That is, magnesium is also 2 plus and iron is also 2 plus. So that is black mica biotite. So this is partial substitution of three-layer structure. I will say again, the normal silicate layers, double, two-dimensional silicate layers, pure silicate layers, are very rare. Normally, they combine with these hydroxide layers and generate two-layer structure or three-layer structure. If you have a two-layer structure with the aluminum hydroxide, it is called colnite. And if you have three-layer structure with the aluminum hydroxide, it is called pyrophyllite. And if you have two-layer structure with the magnesium hydroxide, which is known as white asbestos. If you have three-layer structure with the magnesium hydroxide, that's known as talc. And then when you do partial replacement of silicon in the silicate, in the talc or in the pyrophyllite, you get the micas. And two examples are muscovite and margarite here, pyrophyllite, pilogohite, and then biotite or black mica in the case of talc, partial substitution. Then micas are a bit harder than the talc because of the presence of these extra metal ions which hold the layers together because of the electrostatic attraction. Yet they can be peeled off very easily into layers, and uh, uh, they shine like anything. So third category is Montmorillonite. So this is negatively charged layer. These are negatively charged layers. Unlike the micas, where the positive charge and negative charge are counterbalanced by the cations outside the silicate layer. These are negatively charged layers, but negative charge is lower than the micas. Pyrophyllite is a three-layer structure using the aluminum hydroxide. This is the formula of pyrophyllite. Now the substitution takes place uh, outside in the hydroxide layer. Substitution of aluminum by magnesium, partial substitution. So you get the say 0.33 and 1.667 aluminum, and then hydroxide. This has to be here. Uh, yes, this becomes 2, 1.67 plus this becomes 2, so 2 will not be there, hydroxide. And this the silicate has because of the substitution of the aluminum by the magnesium, this becomes slightly less positive, and therefore the silicate also becomes less negative. So charge is small negative charge is on the silicate layer. So one third of the this monovalent, or one sixth of the divalent, is incorporated between the layers to counterbalance this charge. If the metals are hydrated, minerals are called hydromicas. Hydromicas. These are called as hydromicas. These are another class of these compounds. So talc, we have talc. This is the formula of the talc. Substitution of magnesium in the brucite sheet, which is the brucite, magnesium hydroxide is commonly known as brucite. The substitution of silicon by aluminum. So you do substitution here also and substitution here also. So this type of compounds having NaX, magnesium, aluminum, iron, mixture of the metals here, then hydroxide, silicon, aluminum here. So this is vermicules. It's it spreads and it is formed as worms. It's a lighter material which is used for packing, and it says other use. It's light and transforms itself as worm. That's why the name goes like this. So this is what we discussed last time. I was refreshing it. Now the 3D silicates, when we share all the 4 oxygen atoms in the silicon tetrahedron, there is no charge on the 3D lattice that we generate. We get a network type of structure, diamond type of structure, in which every silicon is linked with 4 oxygens, and each of these oxygens is bridging 2 silicon tetrahedras across the 3-dimensional network. So the example, quartz, cristobalite, these are the examples of the pure silicon tetrahedra forming a network without having any metal atom in its structure, because there is no charge on the lattice network, and therefore no question of existing any metal to have to counterbalance any charge. So there are no metal ions. But isomorphous replacement, many times you replace this silicon in this 3-dimensional network by aluminum. The moment you replace silicon by aluminum, the charge comes in the sheet, and therefore negative charge comes in the silicon lattice, and therefore it has to be balanced by some metal ions as a counter ion. And therefore we get different types of materials depending upon the extent of this substitution and the type of metal ion used to counter that negative charge. So you get 3D silicates with additional cations in the voids, that they generate different types of materials. So replacement of 1/4, for example, 1/4 of the silicon by aluminum in the silicon tetrahedra. This is the formula, general formula written for tetrahedra, but we know that this is SiO4, in which the replacement occurs. So this is, for example, 4 units of the SiO2 generating the formula becomes Si4O8. Then replacement of silicon, 1/4 of the silicon replaced by the aluminum, so it becomes AlSi3O8, 1 negative. Replacement of one silicon by aluminum gives one negative charge. So we have used the 4 units, 4SiO2s. So 1/4 of the 4 SIs is one silicon. Therefore, the formula becomes like this. So large metal ions are used like potassium, sodium, calcium, and barium because the voids are quite large in the size. And the smaller metal ions which were used in the sheet structure or chain structure, iron 3, chromium, manganese, they are in the chain or sheet structure. They are not used simply because of the size. Their sizes are very small. And here in the 3D network, the size of the cavity or size of the voids is large enough. Therefore, you need bigger sized metal ions, potassium, sodium. Sodium is also too small. Potassium is quite common because of its size. And calcium and barium occupy those ones. So these small metal ions are not found in 3D silicates because voids are too large. So replacement of 1/4 or 1/2 of the silicon is common in the 3D networks. So if you have 1/4 of the silicate being replaced, you have this formula, AlSiO8, 1 negative. That 1 negative will be balanced by one positive charge metal ion like potassium, like sodium. Or if you have half of the silicon replaced by the aluminum, then you have formula Al2Si2O8, then you will have two negative charge. Obviously, that will be balanced by either two metal ions of the unit positive charge or a single metal ion of the positive charge. So calcium and magnesium will counterbalance that charge. So there are three types. So this replacement results in three groups of minerals. One is known as feldspars, then is zeolites, and ultramarines. These are the three classes of minerals that are formed by partial replacement of silicon by aluminum in the 3D network of silicate. So feldspars are rock forming animal. They are most common minerals. 2/3 of the igneous rocks are formed from the feldspar. They are important constituents of the granite with small addition of micas. ग्रेनाइट में जो चमक होती है बीच में छोटे छोटे जो स्ट्रक्चर होता है स्टार टाइप ऑफ थिंग्स दे आर माइकास otherwise granite is basically feldspar. So particles and quartz particles are distributed uniformly or non-uniformly. If the distribution of those mica particles or quartz particle is uniform तो ग्रेनाइट की कास्ट बहुत ज्यादा होती है. अगर वो डिस्ट्रीब्यूशन यूनिफॉर्म नहीं है तो वो ग्रेनाइट थोड़ा सस्ता होता है. So because that gives the pattern, the uniformity in the pattern of the distribution of those mica particles, that enhances the aesthetic beauty of the granite and that enhances the cost of the stone. So feldspars are divided into two classes. Orthoclase feldspar, these are in which 1/4 of the silicon is replaced by aluminum and outside obviously we have potassium. Then 1/2 of the silicon replaced by aluminum and outside we have barium. If the cation is potassium or barium, then it is called orthoclase feldspar. These structures are why they are special orthoclase feldspar, because the size of the cations, potassium and barium, they are large cations in their own respective groups. They are large cations and their sizes are absolutely same as the size of the cation. Therefore, the lattice is more or less symmetrical. There is no distortion in the structure of the lattice. So this is more symmetrical because potassium and barium have right size to fit in the lattice cavity or lattice void. That's why they are classified separately as orthoclase feldspar. The other class in which the sodium and calcium ions occupy the voids, they are more distorted. They have more distorted structure because the cations have small size than the size of the cavity, and therefore there is the inherent distortion in the structure. These are known plagioclase feldspar. The albite is example, sodium, aluminium, the same structure in which one quarter of the silicon replaced by aluminium, with the difference that you instead of potassium you have sodium now. So anorthite, this in which half of the silicon is replaced by aluminium, and the coordination outside in the voids we have calcium instead of barium. They are distorted because sodium and calcium are too small than the lattice voids. This is one class of minerals formed by the 3D silicates, in which there is partial replacement of the silicon by aluminum, and because silicate network generates negative charge, it has to be balanced by some positively charged metal ions. These metal ions occupy voids, and the size of the voids is very large, therefore larger metal ions tend to occupy these voids and generate a symmetrical structure, and that is you know orthoplase feldspar. And then the second class is plagioclase and feldspar, which are distorted in the structure because the metal ions which occupy the voids are smaller in size. Then we have zeolites. They are very special minerals with unique porosity. They are very porous and very have voids or cavities, um, which have diverse applications in different fields of the different fields in the industry, and now the people are synthesizing them artificially also because they have diverse applications. So what are zeolites? Zeolites are 3D structures which have cavities of different sizes and different shapes, and they have just like honeycomb structures. And these honeycomb structures have water molecules or some other groups inside occupying those cavities or those voids. And when you heat them as gas, these small molecules occupy them as gas. When you heat that material, that zeolite, these gas are removed from the voids and structure does not break down. That is the beauty. The network does not break down even if those gases are removed. So these materials can serve as ion exchangers. For example, zeolites were originally used for softening of the water. In these voids, they have calcium, sodium atom and potassium atom, and when you add hot water to it, hot water has calcium and magnesium. So calcium is exchanged, magnesium is exchanged with sodium, and the sodium and calcium and magnesium are removed from the water, and sodium gets instead released into the water. So after some time, the zeolite becomes completely packed with calcium and magnesium, and it does not function as a water softener. So it has to be regenerated. So that is done by dipping it or by putting a lot of sodium chloride solution into it, so that calcium ions are removed and sodium ions are occupying again those voids. And then the resin or the ion exchanger, the zeolite, is again ready for functioning as the softener. Similarly, these cavities are having specific size and specific shape many times. So they can serve as molecular sieves. They can retain certain molecules. The zeolites can allow certain molecules to penetrate into those voids, and it will not allow any other molecule which does not fit into the size and shape of that channel. It does not allow the other molecules to pass into those channels, and therefore it can be used to separate molecules, for example, gases. For example, small molecules, ethanol, methanol, carbon dioxide from hydrogen. So these materials have diverse application. They are open structure, they are porous, and yet they are stable. They retain their structural integrity even after heating for some time, and so as to remove the gas molecules from those voids. Many times the gases get condensed in those voids, and then when you heat the material, the liquid turns into the vapors and is removed as the gas, and the zeolite in the process does not break down. It retains its structure. That's how it becomes such an important material. So these are open structure, porous materials. Then the feldspar, they are very much open and porous. And Neumann skeleton is porous and open, penetrated by the channels. There are channels like honeycombs like structure. So channels are large and long. They're long tunnel-like structures, and exchange these are serve as exchange of ions, natural ion exchangers. So nowadays we have the synthetic ion exchangers. The scientists have copied these materials. The zeolites were the first natural ion exchangers, and then the chemists have mimicked this type of structure by generating a 3D type of materials, different polymers, which can serve as ion exchange resins, but they are synthetic. The zeolites are naturally occurring, ion exchangers. They can exchange different ions. Just as one example is softening of the water. So they serve as molecular sieves. They can absorb or lose water molecules quite easily. This process is reversible, and water molecule can occupy those voids or those channels, and when heated, it can be lost also. And the structure of the zeolite does not break down in this process. Water is an example. There are other small molecules like ethanol, methanol, or some gas like carbon dioxide. Water or gas as guest in the cavities. When it loses the water without structure being breaking down, that's how this material becomes so important from practical point of view. So reversible water absorption and loss, zeolites are used in natural ion exchanger and molecular sieves. Molecular sieves means separation process. They can be used to separate different gases, mixture of gases, because certain gases will be allowed to go into those channels, and other molecules, certain gases will not be allowed depending upon the size of the channel and the size of the gaseous molecule. So sodium zeolite was used as water softener. So exchange of sodium by calcium was taking place. No NS sodium zeolite becomes calcium zeolite, and after some times it becomes dead. It does not serve as water softener. Then it has to be regenerated by treatment with the NaCl, and that reverse process takes place. That for during that regeneration process, calcium is being replaced by sodium, and then it becomes ready to function as the ion exchanger again. So we have now synthetic zeolites and synthetic molecular sieves. So to separate carbon selectively, absorb and condense in those channels, carbon monoxide, for example, water, ammonia, ethanol, depending upon the size of the channel. So separation of, for example, straight chain compounds from an isomer which is branched chain. So branched one will not be allowed to penetrate into this the channel, simply because of its geometry, because of its size, because the size of the cavity, size of the channel does not match with the size of the molecule. So this is how the separation is accomplished. So selective removal of small molecules from a mixture, that's how the application of zeolites comes in. Then the last category is ultramarines. These are colored compounds. They were used in the paint industry and the painting, oil paints, painting industry, oil painting, as a colored compounds. So they are silicates again, substituted tetrahedral, 3D silicates in which say silicon has been replaced by the aluminum partially, and this is 6 times. So once the 6 times aluminum has been replaced, you get 6 negative charge on the silicate. That has to be balanced by 6 sodium atoms, and then you have disulfide anion S to 2 negative. That's again balanced by the 2 additional sodium atoms. That's the form. This is blue color pigment used in paint industry. The color is due to the polysulfide ion. So ultramarines or the group of related compounds that contain no water but contain anions outside the silicate, which is chloride, sulfate, or disulfide. So there are many, polysulfides also used, say S4 2 negative, S6 2 negative, different types of sulfide anions. So ultramarines, this is one example. Ultramarine, this is commonly known as ultramarine. Then sodalite, this is again in ultramarine in which you don't have sulfide here but chloride here. Otherwise, rest same. The nosine is again instead of chloride you have sulfate. Ultramarines are also now synthesized. One method of naturally generating synthesis this ultramarine is igniting polynitrate plus sodium carbonate plus sulfur in absence of air. You generate green, blue, or red depending upon what type of polysulfide anion is generated. It is if it is S4 S2 2 negative, it is blue colored ultramarine. If it is S4 2 negative, it may be red colored or green colored depending upon what type of polysulfide anion is generated. So blue pigment is used in paint industry even today or ceramics. It was also previously used in the domestic detergents to give blue color to the clothes to mask the yellowing of the clothes during the washing process. So that is the silicates, how the different structures are generated by substitution and by using different counter ions. You get different compounds with the different appearances, sometimes colors, sometimes different textures, sometimes different appearance, sometimes different strength, depending upon the type of interaction, type of the geometrical arrangement we have in the condensed silicates, and type of the other materials with which they are bounded, the layer structure, particularly the two-layer structure or three-layer structures, the micas that we generate, or these asbestos, pyrophilites, etc., the talc, and then we do substitution in the talc and we get different types of compounds. That finishes all about the first unit. Next time we will start with the second unit tomorrow, hopefully. Thank you very much.
Thank you, sir.
If you have any questions, I'm here for 2-3 minutes. If you have any questions, I'm here. Please go ahead. Is that okay? There are no questions then. Okay, bye. Next, we'll start second unit tomorrow. Thank you very much.
Thank you, sir.
Bye.
Okay, sir. Thank you.